During what would become the most dramatic month in space history, an apocalyptic explosion of near-nuclear magnitude took effect in the Baikonur Cosmodrome in Kazakhstan, 2 weeks before the Apollo 11 landing on the Moon. The Soviet N-1L5 megabooster launched on July 3, 1969, and detonated moments later. The rocket was the Soviet counterpart to the US Saturn V, with the intention to enable crewed travel to the Moon and beyond. Fortunately, only its first stage, the most powerful ever built to that day, ignited, while the rocket crashed back down. Quote, "Today I saw without exaggeration the end of the world, and not in a nightmare, but while fully awake and standing right next to it," Lieutenant Colonel Semen Komarovsky would declare about the massive explosion. The N-1 Moon project was subsequently pushed back 2 years and cost millions in losses. But Soviet officials didn't measure the setbacks in terms of money, but in the precious time they had wasted to win the moon race. On July 5, 1969, only 2 weeks before the Eagle's landing, President Nixon received a presidential daily brief from intelligence officials. Quote, "Deployment of Soviet recovery ships indicated that the USSR would launch a rocket to the moon and bring back samples of lunar soil before the scheduled launch of the Apollo 11 mission." The first indications of the Soviet attempt were the seismic sensors at the location in Baikonur, which the CIA coded as Tyuratam. US intelligence would also be able to listen to countdowns and access telemetry data streams from Soviet missions. In the span of Nixon's presidency, 3 N-1 rocket launches failed, and the United States seemed to take an unquestionable advantage over the Soviet Union in the space race. Nevertheless, technical and policy analyst Charles Vick suggested that, quote, "the race was far closer than publicly perceived, based on declassified intelligence all the way back before Sputnik." By then, US intelligence officials did not know that the July 3rd mission had actually been the second attempt to launch the N-1. The first one had been 5 months before, and it went undetected. The Kremlin watched closely as the Apollo 8 flew around the Moon, the Apollo 9 tested the Saturn V, and the Apollo 10 set the stage for a lunar landing. The Soviets knew they were behind in the moon race even before their first N-1 attempt failed drastically when their 3L launch rocket blew up in February of 1969. The N-1 3L was a super heavy-lift launch vehicle whose objective was to deliver payloads beyond low Earth orbit and eventually land a person on the Moon. By June 3rd, 1 month before the second attempt, top space officials met in Podlipki, near Moscow. The head of the Experimental Design Bureau, Vasily Mishin, assured the attendees that they had learned their lessons from the previous launch disgrace and had protected the cord control system from interference. The N-1 5L was chosen for a new launch, and Mishin was confident it could be sent on a mission around the Moon. Furthermore, Mishin guaranteed that the next 6L mission would launch a full lunar orbiting spacecraft and return safely to Earth, and attributed any setbacks to delays from subcontractors. Mishin's superiors did not believe he was being forthcoming about the many challenges involved. Boris Chertok, chief of flight control system development, supported Mishin, but added that although a 1969 deadline to manufacture and deliver all systems was realistic, further testing would still be required. This board meeting even discussed future missions to Mars. Under warning that any downgrades to the current task should be reported, Mishin continued fantasizing about manned missions to Mars. Still, he did not get any serious attention from the officials. The project's final schedule would be submitted to the Kremlin after re-evaluation from Minister Sergei Afanasyev. Meanwhile, Mishin was allowed to continue his studies on Mars, provided that they didn't interfere with the ongoing 5L mission. The N-1 5L rocket would fly with only some of the recommended changes after the first launch attempt. Further upgrades were put aside, along with the 4L rocket. During a series of meetings held in Tyuratam, Boris Chertok informed his superiors that his flight control team would not be able to prevent the cord network from issuing random commands in case of a similar fire to the 3L. Viktor Litvinov, head of the General Machine Building Ministry, advised Chertok not to mention that detail in their State Commission meeting the next day. Chertok complied and assured Litvinov that he would look into the matter. There was no more time for delays. Vladimir Barman, the head of the launch infrastructure, later proposed developing a program to guide the rocket into the desert in case of miscarriage. He was worried that the expensive facilities could be severely damaged if an incident were to be replicated on the launch pad. Besides the addition of more reliable power generators and a re-evaluation of thermal insulation, further structural reinforcements were needed. This was likely prompted by the results from the first launch, in which an acceleration of 35 g was recorded to press on the ring around the propulsion system on the first stage when all 30 engines reached full thrust. Overall, 10,000 data transmission points were placed on the spacecraft, and the 5L would attempt a circumlunar flight. The State Commission finally met at the main assembly building in Site 112 on May 30th, and Vasily Machine presented all the improvements made on the 5L. The launch was set for July 3rd. To ensure rendezvous with the Moon, the 5L launch time was set at 11:18 p.m. Moscow time. Nighttime was chosen to simplify evacuation, as most workers would have already finished their shift. 2 rockets were raised simultaneously on top of 2 consecutive launch pads at Site 110. On the right pad, the N1, and on the left, a mock-up version for running autonomous and integrated tests. It was a rare sighting at first, but the mock-up was returned to the building before launch for security reasons. Pre-launch preparations went smoothly, though a heat wave affected the personnel. After completion of fueling, all safety pins marked with red ribbons were removed from the vehicle. At the end of the workday, thousands were evacuated around the potential explosion radius. Hundreds of cars and trucks took officers and engineers to safety, along with anything considered of value. A second evaluation occurred by nightfall, when most personnel were relocated to Site 115, the closest safe spot. Special protective trenches were dug out for the occasion. Despite the project's secrecy, many people remained at close range to witness the launch, including locals and personnel family members. Others watched from their rooftops. As the N-15L lifted off from the launch pad, a bright light illuminated the area up to the control center 50 kilometers away. An announcer reported, quote, 5 seconds, flight normal. 10 seconds, flight normal. But suddenly many thrust indicators and the pressure in engines number 1 to 12 dropped to 0. Several pieces started to fall off from the rocket's tail as it froze for a moment while at 100 meters from the ground. The N-1 was the first rocket to have a functional emergency escape system, so when it began to tilt to the side, the engines at the tip fired, conveying the top section to safety. Finally, the gigantic rocket collapsed on the launch pad. Shocked eyewitnesses stared at the enormous red and black mushroom cloud that covered the starry sky above. The area around Site 115 was vibrating and roaring with shockwaves, and the cheerful atmosphere at the Site 10 residential area suddenly succumbed to horror. The lights were turned on even as the launch pad was in flames, and the evacuation process was efficient. Incredibly, no one was hurt. Only 15% of the rocket's propellant detonated, so what could have been a 400-ton detonation only reached 4.5 to 5 tons. Still, it was one of the most powerful artificial non-nuclear explosions in history. The damage caused by the explosion is believed to have cost about 350,000 rubles, but that might be an underestimation. Later investigations speculated about the failure of engine number 8, which exploded a quarter of a second before liftoff. The cord system cut off all the other 30 engines but one, the 18th, whose thrust accounted for the tilting of the entire rocket. Despite several black boxes that captured high-frequency engine parameters being recovered at the site, coming to a definite conclusion proved unachievable. The incident was finally attributed to a foreign particle interfering with the system. However simplistic, no further explanation could be validated. The Soviet bid in the race to send cosmonauts to the Moon had failed, as it would on 2 further missions in 1971 and 1972. The 4 consecutive failures led to the cancellation of the entire N-1 project by decree of the Central Committee of the Communist Party of the Soviet Union. On November 23, 1972, Nixon was given another presidential daily brief that stated, quote, "The Soviets launched their largest space booster, the J vehicle, this morning, but it failed early in flight. It was expected to send an unmanned spacecraft toward the Moon, with recovery either in the Indian Ocean or in the Soviet Union. Because of the continuing problems with the booster, the Soviets' first attempt at a manned lunar landing is not expected until the late 1970s. In an era of incredible military and technological innovations, a Soviet engineer dreamed of bringing light to desolate regions of Russia where nighttime prevails. Vladimir conceived the idea of creating a colossal space mirror capable of reflecting solar light back to Earth. This feat would light entire cities and boost agricultural productivity in Soviet regions where daylight was scarce during the winters. The Znamya satellite faced a lot of opposition from the government and the Soviet space program. Still, Vladimir went public and got the required funds. His dream project was now a reality. The plan was to launch several space mirrors, each larger than the last, until one became permanent. After years of development, Znamya 2 was launched in October of 1992, and for a brief moment in time, it lit a small portion of the Earth. the ambitious Russian project seemed taken straight out of a futuristic movie. Vladimir Soromiannikov was born in Russia on January 7, 1933. From an early age, he was fascinated with the world of engineering and technology. Young Vladimir grew up amidst turbulent times. Joseph Stalin's regime was known for its violent tactics, an iron fist against anyone who opposed him, and continued military and political purges. Stalin's obsession with militarizing the Soviet Union and making it the most efficient industrial and economic bloc in the world had a tremendous toll on its population. Millions of workers were exploited, and Stalin went on to eliminate weekends to bolster productivity. It was also a productive time for ambitious engineers and scientists, as the USSR desperately sought an advantage in technological innovations during the arms and space races with the United States and its allies. Vladimir eventually graduated from the Bauman Moscow High Technical University and the School of Mechanics at the Moscow State University with a degree in engineering. In 1956, he joined the team of engineers at the Korolev Rocket and Space Corporation Energia, who were tirelessly working on the design of the Vostok, the first piloted spacecraft in the history of mankind. After working for over a decade in the space engineering industry, Vladimir eventually became the department head of Energia in the late 1970s. He helped design spacecraft, onboard manipulators, and docking systems. Vladimir also developed the Androgynous Peripheral Attach System, or APAS, which allowed two spacecraft to be coupled either temporarily or semi-permanently. This effective docking mechanism would be used in 1975 to link up the Soviet and American space capsules that were part of the joint Apollo-Soyuz program, the first crewed international space mission. An upgraded version would also be used in the 1990s to dock the shuttle Atlantis with the Mir space station. It was during these years that Vladimir Soromiannikov became fascinated with the idea of solar sails. In 1988, the United States proposed to commemorate the 500th anniversary of Christopher Columbus's arrival to America with a solar sailboat race between the Moon and Earth. Although the US soon discarded the project because of economic reasons, the Soviet Union continued its development through the Space Regatta Consortium, or SRC. This partnership was formed by Energia, Vladimir Soromiannikov, and other Soviet intellectuals. Its objective was to test solar sail technology for future projects. According to author Louis de Guyon from Space Legal Issues, solar sails were, quote, a method of spacecraft propulsion using radiation pressure exerted by sunlight on large mirrors. Vladimir's idea was to design a solar sail system that could use the sun's power to propel a spacecraft through space and reflect sunlight back to Earth during nighttime. Columbia University professor Jonathan Crary would later write in his book 24/7, quote, the scheme called for a chain of many satellites to be placed in sun-synchronized orbits at an altitude of 1,700 kilometers, each one equipped with fold-out parabolic reflectors of paper-thin material. Once fully extended to 200 meters in diameter, each mirror satellite would have the capacity to illuminate a 10-square-mile area on Earth with a brightness nearly 100 times greater than moonlight. Although ingenious, the idea was not novel. German physicist Hermann Oberth and engineer Arnold Ericka had already developed the concept of a space reflector. This giant mirror would reflect sunlight on small parts of the Earth to provide nighttime illumination. However, Oberth's proposal involved developing the mirror as a solar weapon. The intention was for the system to incinerate specific areas or boil entire lakes and rivers. But the project was quickly forgotten during World War II. When Vladimir Soromiannikov first presented the idea to the Soviet space program and the Soviet Union's top brass, he was not taken seriously. The proposal seemed too outlandish, and there were more pressing matters. It was 1988, and the once powerful Soviet Union could not afford to waste more money or funds on projects that would not have a direct and immediate economic benefit. One such concern involved finding a way to increase productivity in agricultural processes in northern regions with long days during summers and extremely short days during winters. To convince his comrades and attract national interest, Vladimir started marketing his solar sail project as a natural way to increase daylight extension. The results would then augment workers' productivity in farmlands. In an interview with the Moscow Times, Vladimir said, quote, we are pioneers in the field. If the experiment goes according to plan, we propose to send dozens more craft into space in the future on a permanent basis. The project attracted so much attention from potential backers that the engineer had to adjust his initial plans. Instead of using the solar sails to power spacecraft, he would now focus on developing the space mirror to light dark zones through the entire planet. Apart from improving overall workers' productivity in northern Russia, Vladimir pointed out that the project would also reduce energy costs in electric lighting and help rescue teams during natural disasters involving hurricanes or tremors. With all this newfound international attention, the Space Regatta Consortium was finally able to put together enough funds to move ahead with the development of the space mirror. In describing the engineer's ambitious plans, Jonathan Crary would write, quote, but the company subsequently expanded its plans to include the possibility of supplying nighttime lighting for entire metropolitan areas. Reasoning that it could reduce energy costs for electric lighting, the company's slogan pitched its services as daylight all night long. Vladimir would later tell the Moscow Times, quote, no more electricity bills, no more long dark winters. This is a serious breakthrough for technology. He named the future satellite the Znamya. Vladimir Seremyatnikov and his team first developed the Znamya, or Banner, as a ground test model. The first Znamya was never sent to space, but it helped perfect the Znamya 2, a 65-foot-wide space mirror. Vladimir's plans were to first launch the Znamya 2, followed by the 82-foot Znamya 2.5, then the 230-foot Znamya 3, and finally a permanent 656-foot mirror installation. A 1993 New York Times article titled "Russians to Test Space Mirror as Giant Nightlight for Earth" detailed the space mirror plans. Quote, "Initial operational systems, using reflectors 650 feet in diameter, would have 24 to 36 mirrors in northern inclination orbits, either 620 miles or 3,700 miles above Earth. A reflector could light a spot by itself, or several could be focused on the same area for continuous illumination or greater brightness, scientists say, producing the light of up to 50 full moons. These mirrors, which would pivot as they passed overhead to keep their light on the same spot, could illuminate surface areas 35 miles to 55 miles across." The Znamya 2 was launched aboard a Progress M15 spacecraft from the Baikonur Cosmodrome on October 27, 1992. After passing through the Mir space station, the Progress spacecraft deployed the mirror next to the space station and produced a 5-kilometer-wide beam of light, seen from southern France to western Russia. The bright spot traveled at an estimated speed of 8 kilometers per second, and although its luminosity was equivalent with that of a full moon, it was only partially seen on land because of excessive cloud cover above Europe. The success of Znamya 2 paved the way for Znamya 2.5, which was expected to light up to 7 kilometers of land with a luminosity equal to 10 full moons. But its main objective was to keep the spotlight at a fixed position for several minutes at a time. Nikolai N. Sevastyanov, a ranking project engineer on Znamya, told the New York Times, quote, "The reflector was a big success because it proved the concept was right. Now we must seek support to build one of bigger size." Znamya 2.5 was launched on February 5, 1999, but as the sail was unfurled, the mirror caught on an antenna from the space station and ripped. Mission Control tried to free the space mirror, but the Znamya deorbited and burned up. Vladimir fought for the ambitious Znamya 3, but the project was abandoned. The government decided that spending on the costly research program was pointless. There was also extreme opposition from environmentalists and scientists who claimed that space mirrors would have detrimental physiological consequences for animals and humans. The engineers still hoped to one day be able to light up to 6 Russian cities with a space mirror. He kept working on the project until he passed away in 2006. Vladimir's intelligence and determination not only earned the respect of Russian space engineers, but also of Americans with whom he worked 2 decades earlier. And since the Russian word for cheese is sir, Seremyatnikov is still fondly remembered as the Big Cheese. In July of 1974, the USSR fired the first and only cannon to be shot into space. Haunted by fears of US spacecraft inspecting or attacking Soviet spaceships and satellites, the R-23M Kartek 23mm cannon had been secretly installed in the Salyut 3 as part of Project Almaz, a top-secret military space station program camouflaged in the cloak of civilian space exploration. Fully armed and operational, the space weapon would remain one of the world's most closely guarded secrets until the fall of the Soviet Union. The United States set off the military space race under a clandestine program intended to secretly establish combat capabilities hidden behind the more public missions of the wider space race. The program was highly classified, with Vice Admiral Richard Truly telling James Bamford from Business Insider, quote, "You just couldn't tell anybody about it. Nobody." Projections and logistics for the program, named MOL, or Manned Orbiting Laboratory, were carried out with the American intelligence community with support from the Air Force and NASA, under the National Reconnaissance Office from 1963 to 1969. Together, the combined forces were tasked with the goal of spying on and opposing the USSR in space. Documents that have since been declassified have allowed the public to access information about the specific objectives and proposals of the operation. Among these was a call for research into methods to take down Soviet satellites by firing projectiles at them or otherwise pushing them out of orbit. The reports even included an elaborate proposal to capture Russian spacecraft by swaddling them in a heat shield material and dropping them back to a research facility in the US for extensive inspection. The Douglas Aircraft Company was contracted to build the MOL, with NASA's Gemini B spaceship potentially serving as a vehicle to take astronauts to and from the station. NASA added a circular hatch that would let astronauts move past the heat shield to enter MOL. The chosen astronauts were only told about the reconnaissance nature of the proposed mission after selection. Budget constraints, however, and an increased focus on civilian missions related to scientific discovery took over, and the MOL was never sent to space. The Manned Orbiting Laboratory was cancelled in 1969, 3 years away from its first planned flight. 7 of the 14 astronauts selected for the program were moved to the Space Shuttle program, and all of them eventually flew to space. The program was cancelled due to the projected potential for cost-effective uncrewed reconnaissance satellites that could carry out the same tasks that MOL was intended for. Yet interference with and destruction of foreign satellites remained an American priority. One method for the US side was even proven in 1985 when an F-15 fighter jet was used to shoot a missile at an outdated US satellite in low orbit. This was officially the only historical case of spacecraft destruction by a weapon. During the development of the MOL, the US prioritized keeping the project a secret, but despite their best efforts, the Soviets discovered at least partially what the US was up to, leading to their own exploration of military space capabilities. The Kremlin launched the top-secret Almaz program at the start of 1960, fearing the military and espionage potential of American spacecraft. Discovery of America's advances with the MOL only served to fuel and push the determination of the USSR to craft its own attack and self-defense space weapons. A respected engineer for the OKB-52 Rocket Design Bureau, Vladimir pushed for the idea of a military space station, and his lobbying efforts were successful in bringing about Project Almaz, meaning diamond in Russian. The manned outpost was primarily intended for reconnaissance, but it would also be armed. Development took longer than planned, as work on heavy payloads and advanced sensors turned out to be more challenging than anticipated. The Soviet military also temporarily lost interest, as their regular satellites were still churning out valuable information. The project was put on hold when NASA announced the launch of its Skylab space station in 1973, which meant the USSR would miss out on setting the first civilian space station. The government and space program decided they needed to beat the Americans and focused on sending a small civilian station partially made with parts of the Soyuz craft and scrapped parts from the planned Almaz station. This new station, called Salyut, was successfully placed in orbit in 1971, attaining a new first for the USSR. Once that political victory was achieved, the Soviet government greenlit continued work on Almaz, camouflaging work on the military stations as part of the Salyut lineup. While American intelligence officials were able to determine some aspect of the truth and could identify which stations were truly civilian, the public remained in the dark about the program. The station was comprised of several sections: the orbital piloted station, the actual space station module, the functional cargo block to dock and load supplies, and the VA spacecraft, the launch and return vehicle for cosmonauts, which could be reused for up to 10 trips. The orbital station would have a diameter of 13.6 feet, or 4.15 meters, and living space of 1,680 cubic feet, or 47.5 cubic meters. 3-man crews would be sent out along with the station by Vladimir Chelomey's Proton rocket UR-500. Once the station was in orbit, they would step into the OPS from the VA through a hatch located in the heat shield, just as the one in the American MOL station. Stays were supposed to last between 1 and 2 months. After the original cosmonauts left, the station would be recrewed and supplied by a TKS resupply craft. Almaz was fully integrated into the Salyut program in order to keep it a secret from the public and from hostile governments. Out of 3 Almaz stations placed in orbit, 2 were successfully crewed. All 3 were launched without their VA spacecraft due to delays in its development and the assembly of the Proton rocket. As the TKS resupply aircraft was never finished, the 2 stations that were crewed received the cosmonauts from modified Soyuz spacecraft. In orbit, the space station only saw those initial visits and withdrawals, with only one of the stations reportedly receiving supplies from an unmanned craft. Neither the VA nor the TKS were ever completed. By 1982, the Soviet Union had placed 7 Salyut space stations in orbit, 3 of which were part of the military's Almaz program. The USSR didn't just intend to only use their military space station for reconnaissance purposes. They also wanted it to be armed with a cannon. The design and construction were given to the KB Teichmaß Design Bureau, headed by Alexander Nudelman, who had overseen several aviation engineering accomplishments after the Second World War. The cannon was an altered version derived from the Tupolev Tu-22's tailgun cannon, the Richter R-23. The original gas-operated revolver autocannon featured on the first Soviet supersonic jet was a 23mm weapon that could fire up to 2,600 rounds a minute. Tweaks to the weapon by Nudelman's team reduced its caliber to 14.5mm. Due to the secrecy surrounding the entire endeavor, certain details of the cannon's capabilities are either speculative or have otherwise not been corroborated. It's alleged that the shot could travel as far as 2 miles, although it's unknown whether this estimate refers to its full capabilities in space. Estimates on the rate of fire vary depending on reports. Theoretically, the modified cannon could fire anywhere from 950 to 5,000 shots per minute, with a safer estimate possibly approaching the 2,600 rate of fire from the original cannon. The projectiles could be shot at a theoretical 850 meters per second, with other reports claiming a slower 690 meters per second. The cannon was tested on Earth, where it was capable of piercing a metal gasoline container placed 1 mile away. The primary challenge for cosmonauts attempting to take down a satellite would be aiming, as the weapon was placed on a fixed mounting, and the entire 20-ton station would need to be oriented towards the target. On January 24, 1975, the Almaz station, camouflaged under the name Salyut 3, was scheduled to be deorbited. The crew had departed from the station several months before, in July of 1974. The USSR had yet to practice actually carrying out a cannon shot in space, and were concerned that recoil, or some other aspect of the untested cannon, would affect the station after firing. Yet now, the conditions were prime for a relatively consequence-free test. Just a few hours before the deorbiting, the test was carried out. The jet thrusters were ignited at the same time the cannon fired, so the expected recoil could be countered. Unofficial reports claimed the cannon shot between 1 and 3 blasts, counting 19 shells in total. The details of the test, and the factual results gathered, remain classified under Russian leadership. After Salyut 3 was deorbited, the Almaz project winded down and was eventually cancelled. By 1982, the Soviet economy was slowing and on its path to collapse, which would still take around 10 years to arrive. The remaining grounded Almaz stations saw a different destiny unfold than the one intended, as 3 of them were launched as Almaz-T, unmanned heavy radar-carrying satellites for reconnaissance purposes. Only 2 worked successfully and stayed in orbit. The hulls of the Almaz 205 and 206 were sold to the private company Excalibur Almaz, which planned to launch them as newly crewed spacecraft in 2015, but in March of 2016, the company announced plans to have its equipment exhibited instead, due to lack of funds. The current location of these Almaz models is unknown. The truth about the Almaz space stations and the fact that one of their cannons was fired were kept secret by Soviet authorities. Limited public access to the subject was only given by Russia after the fall of the USSR. Before the program was cancelled, the Soviet Union had planned to launch a new and improved, possibly more dangerous military space station. The OPS-4 was intended to carry 2 interceptor missiles for space-to-space warfare, instead of a conventional rapid-fire revolver cannon. It was expected to be the 4th military Almaz station. During development, the OPS-4 was modified in terms of design and technology on multiple occasions. It needed a bigger, stronger docking port intended for the TKS spacecraft, which was cancelled in the early stages of development, rather than the lighter port for the Soyuz that the previous 3 Almaz stations had. The station would have seen the introduction of a Mech-A synthetic aperture radar with 3 panels and a manned return vehicle that could be reused. Issues with the return vehicle and TKS made the Soviets replace the idea of the return vehicle for a second docking port. The OPS-4 would have carried a Sheet 2 space-to-space cannon with 2 unguided missiles, but the proposed project was grounded before the scheduled launch in 1978, and then terminated along with the rest of the Almaz program in 1979. Many of the secret details of this highly classified Soviet program remain secret.